Hello all, and welcome to the next session of the course Pre-MBA Statistics. So again, just to give you a brief background about where we are sitting in this week, is that the entire idea has been revolving around the idea of regression modeling or regression fitting or more on prediction. Okay, so these are entirely practical sort of a week. You must have understood by seeing the last couple of sessions. So we started the week by sort of discussing basic ideas about regression modeling, like introducing the parameters beta naught, beta 1, introducing the estimates of the parameters b0, b1, introducing the idea about line of best fit, or which sort of evolved into some other alternative terminologies like least squares line or least squares regression line, line of best fit, etc., etc. Okay, and just in the last session we talked very briefly about correlation measures. We talked about how do you sort of get hold of the line of best fit. So there, if you remember, we tried to minimize a quantity called as summation ei square, which is capital Q, and this is nothing but the sum of squared residual errors. So ei is nothing but residuals for us, which is yi minus yi hat, and then if you square those and then try to take a sum of that, then what we get is nothing but the summation ei square. Okay, and again we sort of took an example about if you have a scatter plot with infinite number of straight lines, then how do you find the line of best fit? Okay, so whichever line which minimizes the summation ei square quantity is called as a line of best fit there. And once you find a line of best fit, it will be a straight line, of course. Then the points on the straight line subsequent to the corresponding yi's are called as yi hats, of course, right? And then on the other hand, you have the observed yi values. Okay, and we started the last session by discussing, or somewhere in between we discussed the idea of line conditions. So linearity, independence, normality, equal variance, right? And again, majority of these four assumptions are on the quantity epsilon I, or the random errors. And why exactly? Because epsilon I is a starting random variable in that unknown population regression line. Okay, and then we sort of argued that since epsilon I is a random variable, my yi or the response also becomes a random variable, and on the other hand we treat the xi's to be fixed or observed fixed quantities. Okay. Alright, and again if you remember vaguely in the last session towards the end, we talked about estimating sigma square. Okay, and again what do you mean by sigma square? So sigma square is also important because sigma square is not the expectation, but sigma square is nothing but the variance of epsilon I. Okay, so since you are assuming epsilon I is to be random variables, there has to be some mean, some variance, some distribution. Okay, by the way, the distribution is normal. It's one of the assumptions in the line conditions, the n condition, normality condition. But again, sigma square is nothing but the variance of epsilon i's, and since this is nothing but the variance of epsilon i's, it sort of translates to variance of the response as well. So estimating the variance of the response is also important there. Okay. Alright, so now moving on, we'll see what could be done in this session. So the next session is called as goodness of fit. So it's a small title, but we'll try to explain what do you mean by goodness of fit, and then we'll sort of deal with the idea of ANOVA subsequently. Okay, and we'll deal with one more measure which sort of tells you if the line of best fit or whatever fit you have or whatever regression model you have, whether it's making good sense or not. Alright, so we'll start with a simple example. So let's say you have the exact same example we've been talking about number of times. So skin cancer mortality rates versus the location where a person lives. Okay, now again very quickly I'll try to give you some notations again. So the red line that you see having a downward slope or a downward trend is nothing but the line of best fit. Okay, which is nothing but yi hat equals b0 plus b1 xi, by the way. Now we'll take a random observation here. So let's say this one right here where the red arrow points. Now again, as far as notations are concerned, the value of y at that point is nothing but the observed response. Okay, and then the value corresponding to that point which sits on the red line right here is called as yi hat, or the predicted response. And by the way, if you see, I've made one more horizontal line roughly around 150 here, which is nothing but the mean of the y values, or rather y bar. Okay, so if you see this quantity is nothing but y bar. So essentially the crux of the matter is that we're kind of breaking down the entire distance of this vertical line between yi and y bar into two parts essentially, isn't it? So here again I can sort of write down the same thing in the form of an equation. So if you look at the LHS, it's yi minus y bar which gives you the entire distance between the observed response and the mean of the y values, and that entire distance could be broken down into two pieces rather. The one of them is yi minus yi hat, the other one is yi hat minus y bar. So, the top one is essentially yi minus yi hat, the first piece, and the second piece really is yi hat minus y bar. Okay. Now, what next? Why is this sort of breaking down the equation into two parts important? So, we will see very soon. Okay. So, from the break in the equation we saw on the last slide, we get hold of number of sum of squares ideas. Okay. So, to be more specific, we get hold of three such sum of squares ideas. On one hand, we have SSR. What do you mean by SSR? SSR is nothing but summation yi hat minus y bar whole square. Now, again let me go back a slide, I will try to explain a bit more. So, let us say if you start with this equation, now assume that you square each of the differences on the LHS as well as on the RHS. So, what exactly you will get? You will get square here, you will get a square here, you will get a square here, and of course, there will be 2 into a cross product term of these two, which one can actually show that's equal to 0. Okay. And once you square them, I will also add a summation sign. So, summation here, summation here, summation here. Okay. So, summation yi minus y bar whole square equals summation yi minus yi hat whole square plus summation yi hat minus y bar whole square. And these are essentially nothing but the three sum of squares that you are seeing on this slide. So, the first one is called as regression sum of squares, which is called as SSR, which is nothing but summation yi hat minus y bar whole square. The second one, which is more important, are called as error sum of squares or SSE, which are summation yi minus yi hat whole square. By the way, let me pause here for a second. This entity or this difference you have seen number of times before. So, can you pause the video and try to tell me that what exactly is the difference there? Yi minus yi hat, just that part. So, yi minus yi hat is nothing but the residual or nothing but the ei. Okay? And hence, these are called as error sum of squares or residual sum of squares. Okay? So, some people also call this summation sum of squares residual sum of squares. So, summation ei square. So, essentially what SSE is nothing but summation ei square. And lastly, the one that you saw on the left hand side of the last equation is called as SST or total sum of squares. Okay. And you have a very nice little equation here that the total sum of squares should equal regression sum of squares plus the error sum of squares. So, SST should always equal SSR plus SSE, and here the main idea is that the cross product term can be shown equal to be 0. Alright, so we will look up at some examples now. So, we will take up a slightly different example. So, a random sample of 35 students gives a relationship between height of the students and the GPA of the students. Okay. So, without plotting anything, without modeling anything, can you just sense that whether this relationship should make sense? Of course not. So, the answer is no, right. I mean, the height of a student has nothing to do with his or her GPA, and this is exactly what you see on the scatter plot as well. Okay. So, if you take height to be the predictor and the GPA to be the response, our sort of a very naive assumption is that we were trying to sort of capture the GPA using the height of a student, which is sort of nonsensical, and again that is being reflected in the scatter plot as well. So, if you see the scatter plot and the red line, so by the way the red line is a line of best fit or the regression line, and it is perfectly horizontal or almost horizontal, isn't it? And we have seen in the last session that if you have a regression line which is almost close to a 0 line, then there is no correlation between height and GPA there. Okay. So, this relationship, to be honest, is not a good one. Okay. And by the way, what do you mean by this horizontal black dashed line? That horizontal black dashed line is nothing but y bar value. Now, here the more important, or rather the most important point to note here in this entire plot is this value that is given here, which is capital R square and not small r square. So, in the last session we talked about small r square, which is the correlation. Okay. And now this capital R square has a slightly more stronger meaning in the context of regression, but of course you see that the value of capital R square is close to 0. So, 0.0028, which suggests that the fit is not good. Okay. So, we'll very soon we'll sort of define what you mean by capital R square there, but just to understand from this very naive little sort of a small example that of course heights and GPAs are not correlated. So, my capital R square value being very close to 0 suggests that the fit itself is not very good. Okay. Alright, so we will take up another example of the very standard skin cancer mortality rate example, and there you might be familiar with this plot. We have been revisiting the same example number of times. So, on the x axis you have the location or the person the location of a person where he or she stays. The response variable is nothing but the cancer mortality rate, and cancer mortality rate in fact is given in terms of deaths per 10 million, while the latitude is at center of state. Now again, the red line is a downward sloped, it has a downward slope trend and is a line of best fit, while the horizontal black line is the mean response or nothing but y bar. But more interestingly, if you see the capital R square value in this context is pretty strong. So it's not close to 0 of course, but it's pretty decent. So close to 0.7, right? So exactly 0.6798, close to 0.7, which is pretty decent. And we'll very soon see that what are the properties of capital R square, but a value of capital R square closer to 1 indicates a very nice fit, while a value of capital R square closer to 0 indicates a not very good fit there. Alright, so this comes to the definition of capital R square, and exactly how is it different from small r square, which is correlation. Okay. So this capital R square is called as coefficient of determination. Alright, so you have a slightly different or slightly fancy term here, is called as coefficient of determination. Small r square was called as coefficient of correlation, while capital R square is called as coefficient of determination. And what does it do? So capital R square is a measure of goodness of fit given by this very easy formula. So you have a very easy mathematical formula to find out capital R square. So capital R square is nothing but SSR divided by SST. And just a short while back we've seen the definitions of all the sum of squares, be it regression sum of squares, error sum of squares, or total sum of squares. Okay. So if you take SSR component, if you divide that by SST component, that ratio is given by the coefficient of determination, which is capital R square. And on the other hand, since you have this relation between SSR, SSE and SST, precisely SST equals SSR plus SSE, right? This is exactly the definition of the equation we saw in the last slide or a couple of slides back. Then from this formula, I can actually write down an alternative formula in terms of the error sum of squares or the residual sum of squares, namely 1 minus SSE divided by SST. Okay. Now what exactly does this capital R square tell us, right? So the capital R square value shows the proportion of variation in y explained by the regression model. Again, one more time. So capital R square shows the proportion of variation in y explained by the regression model. Okay. I'll try to explain number of points here. So firstly, if you take a look at SST formula. So do you guys remember the formula for SST? So SST is nothing but summation yi minus y bar whole square. And now does this sum of squares resemble or sort of look familiar to you? And the answer is yes. So this formula looks familiar to the formula of variance. Okay. And variance in which quantity? Of course variance in y. Of course it's not divided by 1 by n minus 1 or 1 by n, but then regardless of that, it's kind of similar to a formula that we have for variance in y. Okay. So SST quantifies the total variance in the response. Okay. So assume that SST, which is given by this formula, quantifies the total variance we have in the response variable. And again, if you go back to the R square formula, capital R square formula, we have SSR divided by SST. Alright, so what exactly is SSR? So SSR are nothing but sum of squares explained by the regression model, or rather amount of variation explained by the regression model. And then at the end of the day, if you are taking a ratio between SSR and SST, it's nothing but giving you a proportion of variation in the response y explained by the regression model. Okay. So again, just to summarize, so R square is a quantity which sort of measures the goodness of fit of a model, and on the other hand it quantifies the proportion of variance in the total response explained by the regression model. And again, why regression model? Because again, if you go back a slide and then check the formula for SSR, it has yi hat term in that, and yi hat comes from the line of best fit equation. Okay. So yi hat directly translates to how good the model is or how good the fit is essentially. Okay. Alright, now couple of properties of capital R square, again similar to what we had for correlation coefficient. So capital R square sort of lies between 0 and 1 and not minus 1 and 1. So capital R square lies between 0 and 1. If R square is exactly equal to 1, then all the points fall on the line. We have a deterministic relationship, more like Celsius versus Fahrenheit example we saw a couple of sessions back. While on the other hand, if R square is close to 0, the regression line or the line of best fit is perfectly horizontal. Okay. Hence, the value of R square closer to 1 gives a proposition that the model is good or the model is kind of performing very well, while a value of R square closer to 0 gives the understanding that the fitted regression model is not very good there. Okay. Alright, but on the other hand, this capital R square comes with some cautions also. So, some R square cautions to keep in mind. So, whenever R square is close to 0, it does not mean that there exists no relationship. Again, whenever capital R square is close to 0, it does not mean that there is no relationship between x and y. So, what would be a correct statement to make? So, correct statement to make would be that there is no linear relationship between x and y. Alright. So, again in the last session, if you remember, when we talked about correlation, we were pressing on the word linear association, linear relationship between x and y. Similarly here, since the entire idea about fitting a regression line is a linear sort of a model, right, or least squares linear regression line. So, if you see an R square value which is, let us say, close to 0, for example in this example. So, again this is a scatter plot and then R square value is close to 0. So, 0.0003, which of course does not mean that there is no relationship between x and y. It sort of suggests that there is a curved relationship between x and y, isn't it? So, you have a perfect curve there, but not a straight line of course. So, a capital R square value close to 0, again just summarize, does not mean that there is no relationship between x and y. It sort of suggests that there is no linear relationship between x and y. Okay. So, of course in the same example, the appropriate relationship between x and y is in fact quadratic but not linear. And a slightly more interesting sort of a caution that you might have heard about this statement a number of times: correlation does not imply causation. So, firstly, what do you mean by causation? Causation simply means that a particular variable is being caused due to some other variable, or particular variable causes some impact in the other variable. So, you have a simple example here, a slightly interesting one. On the x axis you have wine consumptions or liters of wine per person per year. On the y axis you have heart disease deaths, okay, and per 100,000 people. So, again on the x axis you have wine consumption in liters, on the y axis you have heart disease deaths, and you have a line of best fit, you have a scatter plot between x and y. So, what immediate conclusion can you draw from this scatter plot? So, one immediate conclusion I can draw is that if you consume more wine, of course if you go in that direction, right, the chances of heart disease deaths reduce, which of course is nonsensical, right. So, all of us know that fact, that drinking more wine cannot sort of reduce the heart disease deaths, of course. Okay. So, what might be a problem here? So, again the whole idea is that even though you see a strong R square, by the way R square is almost 70%, which is a decent value to begin with. So, even though you have a capital R square which is that strong, even though you see that the line of best fit is somewhat close to all the points on the scatter plot, but correlation does not imply causation, alright. So, one should not jump to a conclusion that drinking more wine causes less heart disease deaths. So, this last statement I made is not correct. Okay. So, correlation does not imply causation. So, what might be a problem here? So, one problem might be that this wine consumption need not be the only factor which is sort of causing heart disease deaths. I mean, of course, apart from wine consumption, you may have the other demographics of the person, let us say age or weight or height of a person, BMI, other indices, etc., etc. So, one should not jump to a conclusion based on a single factor such as wine consumption when it comes to, let us say, giving a causal relationship between, let us say, two variables x and y there. Okay. So, these are some cautions that one should keep in mind when you are trying to analyze, let us say, capital R square. So, one should always sort of analyze capital R square with a pinch of salt there, right. Alright, now more interestingly, you do have a relationship between correlation and capital R square. So, what exactly is that? So, relationship between correlation small r and capital R square. So, it so turns out that the Pearson's correlation coefficient small r is nothing but plus and minus the under root of capital R square. Again, so the Pearson's correlation coefficient small r is nothing but plus or minus under root of capital R square. So, if your capital R square for model is 0.87, my correlation could be either plus 0.93 or minus 0.93. Now, how do you decide whether the correlation is positive or negative? So, again as we discussed in the last session as well, that the sign of the correlation is implied by the sign of the slope there. So, sign of B1. So, if B1 is positive, my correlation is also positive. If B1 is negative, this should be 0 here. So, my correlation is also negative. So, as long as your trend is upward, you have an upward sloping trend and your slope is positive, my correlation is also positive. And as long as your slope is negative or you have a negative trend, my correlation is also negative there. Alright, and then lastly, one of the other assumptions of the properties is that if capital R square is since lies between 0 and 1, my correlation should lie between -1 and 1 because of the first relationship. So, we all know that the Pearson's correlation is plus or minus the under root of R square. So, if my capital R square lies between 0 and 1, if you take an under root of that, it could be either negative or positive. So, correlation lies between -1 and 1. So, one can either go from this direction to there or from that direction to there, it does not matter. So, you should keep these two small points in mind always, that correlation is a measure which lies between -1 and 1, which sort of gives you in both directions, whether upward slope or downward slope. Whereas, on the other hand, my capital R square is a measure more to do with goodness of fit. So, how good the fit is regardless of the sign. Okay. So, the fit could be either positive, the line of best fit could be either positive or negative, but regardless of the sign of the fit, it tells me how close the points are to the straight line or how good the overall fit is. Alright, now the last bit in this session has to do more with hypothesis tests. Okay. So, again we have discussed or rather spent a lot of time in dealing with hypothesis test in the last week. So, how can you sort of translate some of those testing problems in a regression context as well? Okay. Now, the first statement is by hypothesis test, we are able to translate a scientific question into a statement of hypothesis regarding the parameters in a statistical model. So, again I guess the first is more like a definition of a general hypothesis test. So, by hypothesis test, we are able to translate a scientific question into a statement of hypothesis regarding the parameters in a statistical model. So, I will give you a small example. So, are the chances of having a heart attack same in males versus females? Okay. So, small interesting example, are the chances of having a heart attack same in males versus females? So, how can you sort of solve this problem? So, I can sort of formulate two hypotheses. So, H naught and HA. My null hypothesis would be PM equals PF. Now, what exactly is PM and what exactly is PF? So, PM is nothing but probability of having a heart attack in males, while PF is probability of having a heart attack in females. So, again if you go back to the hypothesis or rather the problem statement here, we are trying to find out whether the chances of having a heart attack is same in males or females, and hence my null hypothesis would be that they are equal. So, probability of having a heart attack in males is exactly equal to probability of having a heart attack in females, and on the other hand the alternative could be as simply they are not equal. So, PM is not equal to PF. So, probability that a male gets a heart attack is different from the probability that a female gets a heart attack. So, at the very beginning we are kind of postulating very sensical sort of hypothesis that PM equals PF or PM is not equal to PF. Okay. So, I think the example you saw on the last slide is just to tell you that how do you sort of formulate a hypothesis. So, depending on a problem in hand, how do you formulate a null hypothesis, then how do you formulate a alternative hypothesis, and so on and so forth. Okay. But now jumping more in a regression context. So, how can you sort of formulate a suitable hypothesis and then test that? Okay. So, again we will start with a simple example. Let us say you have a clinical trial. Okay. So, in clinical trials the question is the effect of a treatment same as placebo? So, for this you should have very basic understanding of a clinical trial. So, whenever let us say a medical firm or medical company wants to roll out a new drug in the market, it has to undergo a set of clinical trials. So, okay, so first let us say on some mice, maybe guinea pigs, then on people, etc., and then from all those clinical trials, so you have different phases in clinical trials. So, through all those clinical trials the medical team understands that how effective the drug is. Okay. And what exactly is a placebo? So, placebo is a tablet or a pill having no ingredients of the exact medicine, but still being administered to patients. Okay. So, placebo, so if a patient is taking a placebo, he or she thinks that they are kind of taking the medicine itself, but in disguise there is no medicine inside a tablet which is called as a placebo. Okay. So, this is exactly how a routine clinical trial takes place. So, you are kind of dividing the sample in two splits, and then you sort of administer the actual drug to one of the groups, you administer a placebo to the other group, and then we can sort of try to answer a number of questions. Okay. For example, the first one that you see here. So, in clinical trials, is the effect of a treatment same as placebo? So, on one hand there is some treatment towards some disease, on the other hand there is no treatment because you are giving a placebo to the patients. Okay. Now, how do you connect the dots with the problem in hand and a regression model? So, let us say you start with this standard regression model yi equals beta naught plus beta 1 xi plus epsilon I, where my xi could be a treatment level, for example 0, 1, 2, 3, 4, where 0 means placebo and yi is the observed response. So, xi are nothing but the levels of the treatment, 0 means placebo and 1, 2, 3, 4 are increasing levels in the treatment, while my yi is the observed response. Okay. Now, here I can make a very simple hypothesis such as my null hypothesis could be beta 1 equals 0 and alternative could be beta 1 is not 0. Okay. So, first let's understand that what would happen if beta 1 is 0. Okay. So, again what would happen if beta 1 is 0? So, again if you come back to this equation, if beta 1 is 0, if this quantity is 0, it means that there is no effect of xi on yi, isn't it? Because this entire quantity would reduce to 0. Alright. So, if beta 1 is indeed 0, there is no effect of xi on yi, whereas if beta 1 is not 0, there would be a significant impact of xi on yi. Okay. So, this is exactly how one can actually test whether there is a significant effect of x and y in a regression model or between two variables or not. And simply how? By simply testing these two hypotheses. So, beta 1 is 0 or beta 1 is not 0. And this sort of the last slide for today would be, so again what you are trying to test here, we are trying to test whether beta 1 is 0 or beta 1 is not 0, and we can actually make a very simple test statistic out of this. So, a very simple test statistic could be B1 divided by the standard error or standard deviation in B1. Okay. And it so turns out that the distribution of the test statistic is nothing but a t distribution with n minus 2 degrees of freedom. So, again you have to go back probably to videos in the last week to understand more about test statistic, distribution about a test statistic and so on and so forth. But if you try postulating these hypotheses which we saw in the beginning, beta 1 is 0 and beta 1 is not 0, the underlying test statistic happens to be B1 divided by standard deviation of B1, which happens to take a t distribution with n minus 2 degrees of freedom, and then I can define a critical value and then you know the drill. So, how do you test the hypothesis out? So, you will be rejecting the null if the absolute value of my test statistic exceeds the critical value. Okay. And what do you mean by that? If you are able to reject the null, it means that beta 1 is not 0, which in turn means that there is a significant relationship between xi and yi, and in the context of the clinical trial it means that the treatment level does make a difference. Okay. The treatment level does make a difference. So, beta 1 is not 0, right. So, the treatment and the placebo levels, they are kind of making a difference in the actual response that you want to predict there. Alright, so just to summarize where we are at, that we talked about a t-test in the context of SLR. So, again remember that we are still focusing on simple linear regression, a single x and a single y. So, the moment you get hold of a single x and single y, a more robust way to find out whether there is a significant linear relationship between x and y is of course to find out R square value, find out correlation value, draw a scatter plot and all those things. But more importantly, we can actually test out a hypothesis whether my beta 1 is 0 or beta 1 is not 0, and if you conclude that beta 1 is not 0, you are kind of concluding that there is a significant relationship between x and y. Okay. Now, in the next session we will spend more time on, let us say, just extending the ideas beyond what we have seen so far and possibly transitioning from SLR to, let us say, MLR, which is multiple linear regression, where we will bring in more than one exercise, and again like I said, we will do very briefly also touch upon a few ideas about diagnostic checking. So, if you remember line conditions from the last session, then how do you sort of verify that all the 4 assumptions are being met by the regression model or not? Thank you.